So to run our first calculation, right, the approach that we have to use is when we're looking at the WebMO job manager, we go here to new job, we click on it, right, there's three different options. We just want to create a new job. So that brings you here to the build molecule tool. So here in the build molecule tool, right, you can build the molecule that you would like to run your computation on in these cases, right? And so if you just simply like click on it, right, it adds a carbon atom and you can add a bunch of them into here, right? So we can just simply make, cyclopentane. In this case, if you wanted to make, a double bond, you can just simply go from one atom to the other. That builds it in. Same thing with a triple bond in those cases. You can hit, Control Z or Command Z for Apple to go back. And so you can have all these parts right here. And so if we wanted to, add a different element into it besides carbon, what we can do here is go to the periodic table, and that loads up all the different atoms that are available, in the periodic table. So if we were like, okay, let's, instead of it being cyclopentane, we can do tetrahydrofuran, so we can add that in here and change one of those atoms now to an oxygen. And so that's set up. And so now, any new atoms that we add, right, are going to be oxygens in these cases. Another thing, that's really important is that we can go here to cleanup. And so under cleanup, right, there's all these different options. So if we click on add hydrogens, those will add the hydrogens based off of the perceived hybridization of the different atoms. That kind of falls apart when we start talking about transition metals, but for organic molecules, this works really well. Another thing that we can do is we can optimize the geometry, right? So there's a few different things. You can change the hybridization. You can select that yourself for atoms. That might be really useful in a scenario where what you're trying to look at is, maybe a radical compound where the hybridization is going to be less, so you don't necessarily want those hydrogen atoms to automatically get added in those instances. But you can also, up it as well. But the next thing we would want to do, right, is we would probably want to optimize it, right? So before, we're going to do a geometry optimization as our first calculation, but if you can optimize it and make the structure look as close as possible to what you think makes the most sense beforehand, that's always worthwhile. And so for that one, I would recommend to use comprehensive mechanics. So what that does is it moves everything around. And so here on this side, you can also like manipulate and look at the molecule. So this thing with the arrow, right, that allows you to rotate it, right? So now we can see THF right here, how this looks like. And so this looks like this right here. If you do the one with the arrows, right, it just simply moves it, translates it around to the magnifying glass, right? Lets you zoom in and zoom out in these cases. And so, there's other things that you can do here as well. You can just do simply the cleanup of the geometry to an idealized geometry by clicking on this part right here. You can change what the symmetry is. You can kind of have it already do some calculations on the orbitals right here, but we're going to be doing a more sophisticated one in our cases in the next step. But, there's a lot that you can, play around with up here as well. So now that this right here is done, right, we have the molecule that we want to, perform our calculation on set up. We would go here to this arrow, and that's going to continue on. Now, one thing I would recommend is just keep it the way it is. You don't have to worry about the symmetry, just because the geometry optimization is going to put it into, the proper positioning for everything. In that case anyways, right? The symmetry isn't going to help. So if we click on OK, that brings us here to the Orca job options configuration menu. So you can put in a job name. And so in this case right here, right, a good way, naming scheme is to give it the name that you have, right? So THF in this case, and then also add in, what type of calculation you're running, right? So in this case, I'm running a geometry optimization. So I'm just going to shorten that down to GeoOpt. So here, then under calculation, you have all these different options. Now, all of these right here are all of the ones that are completely built into WebMO. The only problem is that, they're all optimized for Orca 3, whereas we're using Orca 4. And so some of the keywords and some of the syntax has kind of changed. So I've, fixed all of those. So what you should be using for all of the computations in this class are all the group defined jobs, right? So I have all the ones that we really need to worry about down here. And if there's any additional ones that need to be added, right, you can let me know and I can fix those up and put those here as well. But, we have a geometry optimization that's corrected, vibration frequency calculation that's corrected, proton and carbon NMR calculation corrected, and then also UV-Vis calculation corrected, right? So those are going to be the big ones that we're really going to be looking at. So in this case, we're just trying to do the geometry optimization first. So we just click on geometry optimization corrected. Here now we can choose the method, right? So this is going to be either, an HF calculation, or if we're doing DFT, like we're going to be doing in this class, right? You would then choose the type of DFT that you would want to use. So, the DFT functional that we're going to be using in this case is going to be B3LIP right here. We'll click on that. Next, we have the basis sets. So these are all the basis sets that are traditionally included already. So the def2 SVP, TZVP, and so forth, right? The Karlsruhe basis sets, those are automatically built in to the menu. But if you always wanted to, right, you can click on Other, and that allows you to then add in, manually a basis set that you would want to use. But in this case, right, we're just going to use def2 SVP. You can choose an auxiliary basis set, but we don't really need to worry about that right now. Here you can change the charge, which will be important, right? If you have a charged molecule, right, an anion or a cation. Multiplicity, we'll talk about that in a later video, but essentially that comes down to how many unpaired electrons you have. And then unrestricted, right, determines whether you're doing an unrestricted calculation where you treat each electron individually, or if you're going to be, if it's not clicked, if it's just a restricted one, it treats all the electrons as pairs. Treating electrons as pairs goes a lot faster, and for most molecules that have all the spins paired, that's completely valid. Next, we want to go here to advanced. We click on this right here, and then here's more options that we can look at. And so for now, the biggest option really that we need to change is the number of cores. So it's currently set to 1. We want to change that to 32, right? So that's going to speed up our computation a lot. And so that way we're using 32 processors for our calculations. So that should make it go a lot faster. So now once all of these things are set up, we can just go right here to continue, and that submits our job. And so we can keep an eye here on the status, and that'll change eventually to running, and then it'll count out. And then once it's all counted out, you'll get what the runtime is. Okay, and so now we can see that the computation completed. It only took 40 seconds in this specific case. So now a really good thing to do is actually to download all of the files, so that way you can then upload that into lab archives and have a storage of what your computation is, so that way you can always access it again later if you're not able to access WebMO directly. So to do that, right, we would just simply hit this checkbox right here, go to download and hit job archive. So what that'll do is then download a .tar file, or if you've changed, your setting within utilities to .zip, it'll then change it to that as well. And so you can then take that tar file, right, and directly upload that into your lab archive, so that way you have a storage of those results. But what we'll do in the next video is we can actually look at and we can observe those results and make a lot of figures and a lot of manipulations of the data just simply directly within WebMO. And to do that, we'll click on that magnifying glass right there.